myself J. Ashwini, working as an Assistant Professor of Mathematics, V.V. Vanni Perumal College for Women, Virudhunagar. In this video, we are going to learn about vector spaces. Many physical entities like mass, temperature can be determined by using the real numbers called scalars. But when it comes to measure the velocity of an object or a forces acting at a point, we are in need of the another entity called vectors, which includes both the magnitude and direction. From there arises a new algebraic system called vector spaces. For that, first we see the definition of the vector space. A non-empty set V is said to be a vector space over a field F if it should satisfy two conditions. The first condition is V is an abelian group under an operation called addition, the normal addition which we denote by plus. For V to be an abelian group, it should satisfy the 5 conditions: the closure property, the associative property, the identity element, inverse property, and then the commutative property. Then it has to satisfy 4 axioms to be a vector space. For that, for every element alpha in F and V in V, there is defined an element alpha V in V subject to the following conditions. The first condition is alpha into U plus V should be equal to alpha U plus alpha V. Second condition, alpha plus beta into U equal to alpha U plus beta U. The third one is alpha into beta U equal to alpha beta into U. And the last one is 1 into U equal to U for all U in U. The elements of F are called scalars and the elements of V are called vectors. Now we are going to prove R cross R is a vector space over R under usual addition and scalar multiplication defined by the ordered pair x1, x2 plus the ordered pair y1, y2 equal to the ordered pair x1 plus y1, x2 plus y2, and alpha into x1, x2 equal to alpha x1 into x2. Now we are going to prove R cross R is a vector space. For that, first we are going to prove the abelian group. R cross R is the abelian group. First we are going to prove the closure property. For that, we have to take two elements x1, y1 and x2, y2 in R cross R. For closure property, the sum of these two elements should also belongs to R cross R. We have to prove. For that, x1, y1 plus x2, y2 equal to, as per the definition given in the problem, we have x1 plus x2, y1 plus y2. So which obviously belongs to R cross R since it is given the elements of R cross R in the form of ordered pair. For proving R cross R is associative, we have to take 3 elements in R cross R. That is x1, y1, x2, y2 and x3, y3 belongs to R cross R. To prove it is associative, we have to prove x1 plus y1 plus x2 plus y2 plus x3, y3 should be equal to x1, y1 plus x2, y2 plus x3, y3. Sorry, here comma. We have to prove this condition in order to prove R cross R is associative. For that, first we have to take these two elements and add, which give the result x1 plus x2, y1 plus y2. x1 plus x2, y1 plus y2 plus x3 plus x3, y3, which in turn gives x1 plus x2 plus x3 comma y1 plus y2 plus y3. Already we know that R is an abelian group. So obviously R satisfies the associative property. So if we use the associative property of R, we can easily get these results to get proved. Next we have to prove the identity property. For that, the elements in R cross R is of the form of ordered pairs. So the identity element will obviously in the form 0, 0 in R cross R, which belongs to R cross R, since 0 is the identity element of R. For inverse, if you add an element, any element in R cross R, you should get the identity element, which is the law for inverse property. So if you add minus x1 comma y1, then we will get the identity element of R cross R. So minus x1 comma minus y1 is the inverse element of x1 comma y1 in R cross R. And the last one is commutative. For that, we have to take again two elements, x1 comma y1 plus x2 comma y2, which should be equal to x2 comma y2 plus x1 comma y1. This one can be obviously proved since R is commutative. So if you add these two things, you will get x1 plus x2 comma y1 plus y2. Since R is commutative, we can interchange the elements and get y2 plus x2 comma y1 plus x1. From that we can get our desired result. So the first condition is proved here. For proving the four axioms, the first axiom is, as per our definition, alpha into u plus v equal to alpha u plus alpha v. So instead of u and v, here we are going to take x1 comma y1, which is equal to u, and v, which is x2 comma y2. So we have to consider alpha into x1 comma y1 plus x2 comma y2, which is equal to alpha into, if you add, we get x1 plus x2 comma y1 plus y2. So as per the scalar multiplication definition, alpha into x1 plus x2 comma alpha into y1 plus y2. If you multiply alpha inside, you get alpha into x1 plus alpha into x2 comma alpha into y1 plus alpha into y2. So now we can make it as an ordered pair, alpha x1 comma alpha y1 plus alpha x2 comma alpha y2. So when we take alpha as common, alpha into x1 comma y1 plus alpha into x2 comma y2, which is obviously alpha u plus alpha v. So the first axiom is proved. For the second axiom, we have to prove alpha plus beta into u equal to alpha u plus beta u. Instead of u, we are going to take the ordered pair x1 comma y1. So alpha plus beta into x1 comma y1 equal to, by using the definition of scalar multiplication, we have here alpha plus beta into x1 comma alpha plus beta into y1, which is equal to alpha x1 plus beta x1 comma alpha y1 plus beta y1. So which is equal to alpha x1 comma alpha y1 plus beta x1 comma beta y1. which in turn alpha into x1 comma y1 plus beta into x1 comma y1. So alpha plus beta into x1 y1 equal to alpha into x1 y1 plus beta into x1 y1. The third one is alpha into beta u equal to alpha beta into u. So alpha into beta x1 comma y1 equal to alpha into beta x1 comma beta y1, which is equal to alpha beta into x1 comma alpha beta into y1, which is equal to alpha beta into x1 comma y1. And the fourth one is 1 dot x1 comma y1 will obviously be equal to x1 comma y1. So therefore the four axioms are satisfied. Therefore R cross R is a vector space over F. The next is, let V be the set of all ordered pairs of real numbers. Here addition and scalar multiplication are defined by the same one, ordered pair x1 comma x2 plus y1 comma y2 equal to ordered pair x1 plus y1 comma x2 plus y2. The scalar multiplication is slightly vary from the previous problem, that is alpha into x1 comma x2 equal to x1 comma alpha x2. Here we have to prove V is not a vector space over R. In the two conditions, the abelian group will not get affected here since the addition is defined as the same as previous one. So we will get surely V is the abelian group. But when it comes to the scalar multiplication, the definition is a slightly different one. So for the four axioms we have to try to prove any one is not satisfied. Here also we have to consider the first axiom, that is alpha into u plus v, the two elements x1 comma y1 plus x2 comma y2, that is alpha into x1 plus x2 comma y1 plus y2. As per the definition of scalar multiplication here, alpha into x1 plus x2 comma alpha into y1 plus y2. So which is equal to x1 plus x2 comma alpha y1 plus alpha y2. So which in turn equal to x1 comma alpha y1 plus x2 comma alpha y2, which is equal to alpha into x1 comma y1 as per the definition of scalar multiplication, alpha into x2 comma y2. So with respect to this axiom, we get it is proved. So we have to go for the second one and check, that is alpha plus beta into u. Consider alpha plus beta into x1 comma y1, which is equal to x1 comma alpha plus beta into y1 as per the definition of scalar multiplication, which is x1 comma alpha y1 plus beta y1. Here we have only one element here. Here we are having some of the two elements. So we have to consider the right side and try to prove both of them are equal. If we get both of them are equal, then we can say the second axiom is satisfied. For that we have to consider alpha into x1 comma y1 plus beta into x1 comma y1, which in turn equal to x1 comma alpha y1 plus x1 comma beta y1, which is equal to x1 plus x1 comma alpha y1 plus beta y1. Here if you see, this is the answer we have got for the left hand side simplification and this is got for the right hand side simplification. Both of them are not equal. Therefore the second axiom, alpha plus beta into x1 y1 equal to alpha into x1 y1 plus beta into x1 y1 is not satisfied. Therefore V is not an abelian group. Sorry, V is not a vector space. So now we have seen the definition of a vector space and one for an example of a vector space, one not for an example of vector space. Thank you.